Jai Hind everyone. Today we'll see the part 2 of the chapter 4 of NCERT Class 11 Physical Geography. In the previous video, we learned, I've explained the details of continental drift theory regarding the process and evidences that support the theory and also the forces for drifting of the continents. And also we have seen briefly the convectional current theory also. Next, let's move and we'll resume from mapping of this ocean floor. Mapping of the ocean floor. Detailed research of the ocean configuration revealed that the ocean floor is not just a vast plain, but it is full of relief. What does it mean that it is full of relief? It means we may find mountains, we may find plateaus or slopes. We'll see what the relief comprises. Expeditions to map the oceanic floor in the post-World War II period provided a detailed picture of the ocean relief and indicated the existence of submerged mountain ranges as well as deep trenches, mostly located closer to the continent margins. So, in mountain ranges, they are the highest points, they are the highest elevated structures. But when it comes to deep trenches, these are the deepest points, we can say. And where are these located? These are located closer to the continent margins. The mid-oceanic ridges were found to be most active in terms of volcanic eruptions. Which are active mid-oceanic ridges. The dating of the rocks from the oceanic crust revealed the fact that they are much younger than the continental areas. So, according to the carbon dating of the rocks, it is revealed that oceanic crust is younger than continental areas. Rocks on the either side of oceanic ridge and having equidistant location from the crust were found to have remarkable similarities. What does it mean? We'll see. Here, if you see, if this is the crust, if it is the ridge, and if we move from here and if we move from here, the 2 points, let's say this is one point and this is another point. If they are equidistant from the crust, then it is said that the properties of that rocks that are equidistant from the crust and also the age are similar. So this means the floor is spreading. What is that? We'll learn about it. In ocean floor configuration. In this section, we shall note a few things related to the ocean floor configuration that help us in the understanding of the distribution of continents and oceans. The ocean floor may be segmented into 3 major divisions based on the depth as well as the forms of relief. So how many divisions? 3. These are continental margins, deep sea basins, and mid-oceanic ridges. So the 3 major divisions are based upon the depth and as well as the forms of relief. These are continental margins, deep sea basins, and mid-ocean ridges. What are continental margins? These form the transition between continental shore and deep sea basins. So, they include continental shelf, continental slope, continental rise, and deep oceanic trenches. So, what are all included in continental margins? Continental shelf, continental slope, continental rise, and deep oceanic trenches. Of these, the deep oceanic trenches are the areas which are of considerable interest in so far as the distribution of oceans and continents. So, among all these that mentioned and comprised of continental margins, deep oceanic trenches are the most or of considerable interest. Next, the next division is deep sea basins or abyssal, which are also called abyssal plains. These are extensive plains that lie between continental margins and mid-oceanic ridges. So, between continental margins and mid-oceanic ridges lie the abyssal plains. These are the areas where the continental sediments that move beyond the margins get deposited. So if we see the sediments are getting deposited, then we can say it is fertile and also contain fossils. And the next third and last division is mid-oceanic ridges. This forms an interconnected chain of mountain system within the ocean. It is the longest mountain chain on the surface of the earth, though submerged under the oceanic waters. So which is the longest mountain chain on the surface of the earth? It is mid-oceanic ridge, although it is submerged under the oceanic waters. It is characterized by central rift system at the crust, a fractional plateau, and a flank zone along its length. The rift system at the crust is the zone of intense volcanic activity. As we read before, that the crust is the most active part of volcanoes. Here, the rift system at the crust is the zone of intense volcanic activity. Next, distribution of earthquakes and volcanoes. Let's see the figure 4.2 once. So here, if you see the smaller dots, these are the volcanic eruptions, but the longer spots are all called hot spots. And the spots in gray color, they are called deep earthquake zones. And the one with, these are shallow earthquake zones. And the shaded part is the deep earthquake zones. If you see here, you can see a shape like this that goes from the tip of South America along the North America, and then that goes through Japan, islands, and again till Southeast Asia. This is called Pacific Ring of Fire. It is also in the shape of horseshoe, and it is called Pacific Ring of Fire that circumvents the Pacific Ocean. So this is called Pacific Ring of Fire. Now we'll come to the distribution of earthquakes and volcanoes. Line of dots in the central parts of the Atlantic Ocean, almost parallel to the coastlines. It further extends into Indian Ocean. It bifurcates a little south of Indian subcontinent, with one branch moving into East Africa and another meeting a similar line from Myanmar to New Guyana. Here, this one. You will notice that this line of dots coincides with the mid-oceanic ridges. The shaded belt showing another area of concentration coincides with alpine Himalayan system and the rim of Pacific Ocean. In general, the foci of the earthquake in the areas of mid-oceanic ridges are at shallow depths, whereas along the alpine Himalayan belt as well as the rim of Pacific, the earthquakes are deep-seated. So we will see one difference here between regarding the foci. So foci of earthquake in the areas of mid-oceanic ridges, that is in the sea here. If we see it here, the foci is of shallow depth. But along alpine Himalayan belt and also rim of the Pacific, the earthquake foci are deep-seated ones. The map of volcanoes also shows a similar pattern. The rim of the Pacific is also called rim of fire due to existence of active volcanoes in this area. So the rim of the Pacific is also called rim of fire. Next, we'll learn the important concept of seafloor spreading. Before we read that the rocks which are equidistant from the crust are similar in properties and also in age. Now we'll learn the reason behind it. As mentioned above, the post-drift studies provided considerable information that was not available at the time Wegener put forth his concept of continental drift. Particularly, the mapping of ocean seafloor and paleomagnetic studies of rock from oceanic regions revealed the following facts. So these are the conclusions that have been made after mapping the oceanic floor and paleomagnetic study of rocks from oceanic regions. The first fact is, all along the mid-oceanic ridges, volcanic eruptions are common and they bring huge amounts of lava to the surface in this area. When the lava, due to volcanic eruptions, what happens when a volcano erupts? It brings out loads and loads of lava from the mantle region into the crust. So this it is realized that along the mid-oceanic ridges, volcanic eruptions are common. Next, the rocks equidistant on either sides of the crust of mid-oceanic ridges show remarkable similarities in terms of period of formation, chemical composition, and magnetic properties. Rocks closer to the mid-oceanic ridges have normal polarity and also they are the youngest. The age of rocks increases as one moves away from the crust. The rocks which are closer to the mid-oceanic ridge also show polarity and they show similarity to the parent rock, that is the mid-oceanic ridge. But as they move away from it, they develop their own they develop their own properties. Then the oceanic crust rocks are much younger than the continental rocks. This is the third fact. The age of rocks in the oceanic crust is nowhere more than 200 million years old. Some of the continental rock formations are as old as 3,200 million years. So we can it is said that ocean rocks are younger than continental rocks. Then fourth one is the sediments on the ocean floor are unexpectedly very thin. Scientists were expecting, if the ocean floors were as old as the continent, to have a complete sequence of sediments for a period of much longer duration. But nowhere was the sediment column found to be older than 200 million years. So the sediments on the ocean floor is extremely thin. The fifth one is the deep trenches have deep-seated earthquake occurrences, while in the mid-oceanic ridges, the earthquake foci have shallow depths. Before we learned, in the Alpine Himalayan belt and the rim of Pacific, the earthquake foci have deep-seated one. Now we can include deep trenches also, which have deep-seated earthquake occurrences. While in the mid-oceanic ridges, the earthquake foci have shallow depths. Next. These facts and a detailed analysis of magnetic properties of the rocks on either side of mid-oceanic ridge led Hess to propose his hypothesis known as seafloor spreading. So who gave seafloor spreading? It was given by Hess in 1961 based on the studies of based on analysis of magnetic properties of rock on either side of mid-oceanic ridge. Hess argued that constant eruptions at the crust of oceanic ridges cause the rupture of oceanic crust and the new lava wedges into it, pushing the ocean crust on the either side. The ocean floor thus spreads. What does it mean? If you see here, when the volcanic eruption takes place here, here the lava wedges into it, thus making the seafloor move this way and making the seafloor move this way. As they reach a point where they have to come up in contact with continent, instead of moving the continent, they start getting subducted. So they start from here, they move away from the ridge, move away, and they start subducting. So this is how the seafloor spreads. As the new lava wedges into it, a new ocean floor is being made here, and the old ocean floor is getting subducted here. So this is called the seafloor spreading theory given by Hess in 1961. The younger age of the oceanic crust, as well as the fact that the spreading of one ocean does not cause the shrinking of the other, made Hess think about the consumption of oceanic crust. He further maintained that the oceanic floor that gets pushed due to volcanic eruptions at the crust sinks down at oceanic trenches and gets consumed. This is the basic concept of seafloor spreading. The next theory is plate tectonics. The plate tectonics is given by Mackenzie, Parker, and also Morgan in 1961, who independently collected the available ideas and came out with another concept called plate tectonics. Oh, first of all, we have to learn the meaning of tectonic plate. What is a tectonic plate? A tectonic plate, which is also a lithospheric plate, is a massive, irregularly shaped slab of solid rock, generally composed of both continental and oceanic lithosphere. So, tectonic plate is basically a fragment of the lithosphere, which is not exclusively either oceanic lithosphere or continental lithosphere. It can compose both. Plates move horizontally over the asthenosphere as rigid units. The lithosphere includes the crust and the top mantle with its thickness varying between 5 and 100 kilometers in oceanic parts and about 200 kilometers in the continental areas. So from this we can say that oceanic tectonic plate is thinner than a continental plate. A, a plate may be referred to as continental plate or oceanic plate depending on which of the two occupy a large portion of the plate. So if the lithospheric plate has more continent on it than the ocean, then it is called a continental plate. Otherwise, it is called an oceanic plate. The Pacific, we'll see one example here. Pacific plate is largely an oceanic plate, whereas the Eurasian plate may be called as a continental plate because we know the reason. The Pacific plate comprises mostly of the Pacific Ocean waters, while the Eurasian plate, we know it is a continent. The theory of plate tectonics proposes that Earth's lithosphere is divided into 7 major and some minor plates. Young fold mountains, ridges, trenches, falls surround these major plates. We'll see what are the major plates. So first, how many major plates the plate tectonic theory proposed? 7. In that, the first one is Antarctica. This all Antarctica plate and the surrounding oceanic plate. And the next one is North American with Western Atlantic floor separated from South American plate. If you see here, North American and the Western Atlantic Ocean cut along the South American plate with Caribbean plate. The third one is South American with Western Atlantic separated from North American plate along the Caribbean plate. So this is the South American plate. It is divided from North American along the Caribbean plate. The fourth one is Pacific plate. And the fifth one is India, Australia, New Zealand plate. What is that? We'll see. One second. Here, if you see here, this is India, Australia, New Zealand plate. So it comprises the Indian subcontinent, Australia, and also the surrounding Indian Ocean waters. And the next one is Africa with Eastern Atlantic floor plate. So this is the African plate along with Eastern Atlantic floor plate. This is the African plate. And the next one is Eurasia with adjacent oceanic plate, which is the Eurasian. This comes all the way from here till here. So these are the 7 major plates that are proposed in plate tectonic theory. And some of the minor plates are listed below. We will see that also. The first one is Cocos plate. Next, we'll see where the Cocos plate is. It is here, between North and South Africa along the Pacific Ocean. Next, we have Nazca plate. Nazca is adjacent to the eastern coast of South America. Next one, we have Arabian plate. Where is Arabian plate? Here it is Arabian plate. And the next one is Philippine plate. Philippine, here, above Australia. And the fifth one is Caroline plate. Where is Caroline? Here, to the left side of Philippines plate. So these are the minor plates that are proposed in the theory. And Indian plate. We also have Indian plate. Next. These plates have been constantly moving over the globe throughout the history of the Earth. It is not the continent that moves as believed by Wegener. Continents are part of a plate and what moves is the plate. Moreover, it may be noted that all the plates without exception have moved in the geological past. Wegener had thought of all continents to have initially existed as a supercontinent in the form of Pangaea. However, later discoveries reveal that the continental masses resting on the plates have been wandering all through the geological period, and the Pangaea was a result of converging of different continental masses that were parts of one or the other plates. Scientists using the paleomagnetic data have determined the positions held by each of the present continental landmass in different geological periods. The position of Indian subcontinent, mostly the peninsular India, is traced with the help of rocks analyzed from Nagpur area. I think this is a point because how is the position of Indian subcontinent traced? With the help of rocks analyzed from Nagpur area. Then we need to learn about the three types of plate boundaries. The first one is divergent boundaries. The divergent boundaries are also called constructive boundaries because with their movement, a new crust is formed. In divergent boundaries, new crust is generated at the plates as they pull away from each other. The sides where the plates move away from each other are called spreading sides. The best known example of divergent boundaries is the Mid-Atlantic Ridge. Here. So this is the divergent boundary. Examples about for the boundaries I think is important when coming to examination. So we need to be updated about that also. So we'll see the different where the different divergent boundaries are found in the world. The first one is along Mid-Atlantic Ridge, as given here. So Mid-Atlantic Ridge, at this the American plates are separated from the Eurasian and African plates. And the next one is convergent boundary. Convergent boundary is also called a destructive boundary because the crust is destroyed as one plate dived under other. The location where sinking of a plate occurs is called a subduction zone. If you see here, the oceanic crust is getting subducted under the continental crust. So this is an area of convergence. We have three types of convergence, that is oceanic continental plate, between two oceanic plates and between two continental plates. In seafloor spreading, we can see the example of oceanic and continental convergence, and the other two are between two oceanic plates and between two continental plates. And the next one is transform boundaries. In transform boundaries, along the transform boundaries where the crust is neither produced nor destroyed as the plates slide horizontally past each other. Transform falls at the planes of separation generally perpendicular to the mid-oceanic ridges. So these transform falls are generally perpendicular to the mid-oceanic ridges. As the eruptions do not take all along the entire crust at the same time, there is a differential movement of a portion of the plate away from the axis of Earth. Also, the rotation of the Earth has its effect on the separated blocks of the plate portions. Now we'll see how fast or how slow these plates move. The strips of normal and reverse magnetic field that parallel the mid-oceanic ridges help scientists determine the rates of plate movement. So how do scientists determine the speed of plate movements? By strips of normal and reverse magnetic field that parallel the mid-oceanic ridges. These rates differ. If we see Arctic ridge has the slowest rate, which is less than 2.5 centimeter per year. But when it comes to East Pacific rays near Easter Island, which is in Pacific Ocean. Along here, Easter Island, if we see here, East Pacific rise near Easter Island in the South Pacific, about 3,400 kilometers west of Chile, has the fastest rate, that is more than 15 centimeter per year. So which is the slowest moving plate? That is Arctic ridge, which has less than 2.5 centimeter per year. And the fastest one is East Pacific rise, which has the rate of 15 centimeter per year. As we learned the rates of plate movement, but now we'll see the force that is responsible for the plate movement. When the Wegener had given the continental drift theory, most scientists believed that the Earth was a solid, motionless body, but the concepts of seafloor spreading, Unified theory of plate tectonics have emphasized that both the surface of the earth and the interior are not static and motionless, but they are dynamic. What does it mean? There is a motion in the crust and the interior of the earth. The fact that the plates move is now a well accepted fact. The mobile rock beneath the rigid plates is believed to be moving in a circular manner. The heated material. The heated material rises to the surface, and along the surface it spreads and begins to cool and then sinks back into deeper depths. And this cycle is repeated over and over to generate what scientists call a convection cell or convective flow. So this cell or this flow, this cycle is called convection cell or convective flow. But how do the matter inside the interior of the earth get heat so that this cycle can be repeated or this cycle can be done? So the heat within the earth comes from two main sources. One is radioactive decay and residual heat. Arthur Holmes first considered this idea in the 1930s, which later influenced Harris Hess thinking about seafloor spreading. The slow movement of hot, softened mantle that lies below the rigid plates is the driving force behind the plate movement. So this is the reason this cycle is being continued, and because of this the continental plates are still today being moved. So this is all about today's class. We'll meet in the next video. Thank you.